Hi, and welcome to the video lecture series on contact mechanics in the course M7033T, Scientific Computing with Applications in Tribology. My name is Andreas Almqvist and I work in the Division of Machine Elements here at Luleå University of Technology. This is the fourth part of the first video lecture on contact mechanics fundamentals, and here you will learn about the subsurface stress field and how friction and roughness affects the situation underneath the surface. So this lecture starts by looking underneath the surface, and we will connect the stress field to a Hertzian pressure distribution on top of the surface, and then we will look at what happens when we add traction via friction on the surface, how that changes the stress development. And then after this we look into what is really interesting to see, and that's how roughness affects the stress situation underneath the surfaces. Due to that pressure acting on the surface on the boundary of the elastic half space, we will also see development of stresses inside the materials, i.e. subsurface stresses. And here we see a figure which I copied from the book by Anton van Beck called Advanced Engineering Design. And it shows, for instance, that the shear stress tau is having a maximum value at a distance of about 0.48 A, where A is the Hertzian radius of that Hertzian contact. In connection to this, if the parabolically shaped half space is pressed against the other one under the load W, then the maximum pressure will be the Hertzian pressure, and it will be given by the expression we see here to the left. And we can also compute the average pressure in a similar way. What happens when we add a little bit of friction can be seen here. So on the leftmost figure we have zero friction, another case that we saw before, and now we see the column map of the shear stresses below the surface. So we see the characteristic that it has a maximum at approximately half of a Hertzian radius. When we add a little bit of friction, Coulomb friction, mu equals 0.3, and then we have a tangential traction on the surface, tau equal mu p, then this shear stress distribution shifts a little bit to the right, and the maximum moves both to the right and a little bit upwards. And this is more and more pronounced as we increase the friction. The change caused by the friction without any roughness was quite small compared to what happens when we add a little bit of roughness, as can be seen here. So on the leftmost figure we see the stress field for a relatively smooth but yet rough Hertz case. So we have the parabolic profile, and then we have added some roughness on top of that. Due to the parabolic profile, we see that there is a sort of a maximum still at half of a Hertzian contact radius beneath the surface, but due to all the small asperities contacting that half space, we get small shear stress concentrations very near to the surfaces, and that's because of the asperity's small radius itself. So it can be seen as a nearly independent Hertzian contact, and therefore that has a small radius, and the small radius causes the shear stress maximum to occur very near the surface. And this is more and more pronounced as we increase the magnitude of the roughness, and this is done here from left to right by increasing the RA value of the the surface. So the average roughness value. But still, you can see it's a seemingly small roughness value of only 28 nanometer on the rightmost figure. But we have lost all of that Hertzian, nominal Hertzian shear stress field, which gives rise to the stress maximum at half of the Hertzian contact radius A.